We've mapped out the physical architecture of a large language model. We know it relies on tokens, which are fragments of words converted into data. We've seen embeddings, the mathematical coordinates that give those tokens meaning, and transformer blocks, the layers of computation that process them. But that leaves a massive unanswered question. How did the billions of connections inside this digital architecture actually acquire the precise values needed to mimic human reasoning? This complex machinery operates on a singular foundational objective, a statistical game predicting the next word. When fed a prompt like, "The capital of France is blank," the AI assigns probabilities to multiple answers, weighing Paris against London. Assigning high probability to the wrong word registers a mathematical error. The training goal is minimizing that error margin. Every seemingly magical conversation, every complex block of code an AI generates, is rooted entirely in mastering this single microscopic statistical objective. To get good at predicting the next word, the model needs to consume human knowledge. It is fed an incredibly diverse diet of web pages, published books, news articles, and raw code. Before the model even sees this text, engineers clean out the digital noise and chop the raw data into billions of standardized token sequences. Inside the model are parameters. Parameters are adjustable internal numbers, or weights, that act as the system's memory and logic pathways. This flowchart breaks down the active training loop. The model ingests a batch of token sequences, makes its predictions, and calculates its overall error rate, which engineers call loss. Loss is simply a numerical score of how far off the model's predictions are from the actual text. To fix those errors, the system uses gradient descent. Gradient descent is a mathematical technique that sends a signal backward through the network to pinpoint exactly which parameters caused the bad guess. That backward signal subtly nudges those billions of individual parameters in the right direction. The system physically alters its internal pathways, resets, and processes the next batch of data with slightly sharper precision. The AI is not memorizing documents. It is continually sculpting billions of mathematical weights, trial after trial, until the underlying patterns of human language are baked directly into its structure. Moving from digital math to physical reality, this optimization loop demands massive infrastructure. These server farms are packed with GPU clusters. GPUs, or graphics processing units, are specialized chips capable of performing thousands of calculations simultaneously. The prediction loop we just looked at has to be repeated across trillions of distinct tokens. To handle that load, thousands of GPUs or TPUs must run in perfect parallel synchronization. TPUs are tensor processing units, custom-built hardware designed specifically to accelerate machine learning workloads. Even with warehouses full of specialized hardware working in tandem, a single continuous training run can take weeks or sometimes months to finish. That massive physical footprint creates an immense economic bottleneck. Only a very small handful of highly capitalized organizations possess the infrastructure required to build these foundational models from scratch. The power of modern AI originates from the sheer brute force scale at which this microscopic statistical rule is executed. The industry has a formal term for this entire resource-intensive macro-scale process: pre-training. The direct result of pre-training is a base model. This is a highly capable, general-purpose system that has absorbed a broad understanding of world knowledge and language formatting. Before a base model is ever released, engineers put it through rigorous safety evaluations. They benchmark the raw model to measure its tendency to hallucinate false information, and they actively filter out harmful biases. But the base model has a distinct limitation. While it possesses vast foundational intelligence, it is essentially a jack-of-all-trades. It isn't specialized for specific high-value tasks. This diagram shows the next crucial step. Developers take that massive generalized base model and branch it off into focused specialists. They adapt it to become dedicated coding assistants, legal document summarizers, or targeted customer support bots. Pre-training builds the raw, powerful foundation of the system, but it is the subsequent step of customization that actually gives the machine a job. Thanks for joining us on this journey through the massive machinery of pre-training. We are Knowledge Equity Partners. Our mission is to provide multilingual, contemporary knowledge that enhances your daily efficiency. If you found this valuable, please subscribe, like, and share. Keep your curiosity sharp and continue learning alongside your peers. In our next episode, Episode 7, we'll show you exactly how developers take these massive base models and fine-tune them for your personal and business use cases. We'll see you then.